Hi everyone, today is January 14th. This is the hard data integral for today. Please pause and try it out for yourself and we'll start. So we need to find I such that I is not equal to 0 and I satisfies this equation right here. So we're going to do this using Feynman's technique. We'll let I of alpha, so we're going to make I into a function of alpha with the integral from 0 to infinity of 1 minus e. Notice that there's an x squared in the denominator. We want to really remove this x squared, so we'll let alpha be here with e. So we have e to the negative alpha x squared. So when we differentiate, this x squared will be gone, dx. Now let's see what our initial condition is. Let's let alpha be equal to 0, and we'll get the integral from 0 to infinity of 1 minus 1 over x squared dx. This is 0. So this gives us what we need to apply Feynman's technique. So let's differentiate, and we'll have the integral from 0 to infinity, the partial derivative with respect to alpha of 1 minus e to the negative alpha x squared over x squared dx. This partial derivative, well, 1 is a constant, so we don't need to worry about that, and then we'll get negative x squared. The x squareds will cancel out, and we'll have e to the negative alpha x squared dx. Now we need to know the value of this integral. Okay, this integral is really just a Gaussian integral with alpha x squared instead of having only x squared. So let's do a substitution. Let's t be equal to the square roots of alpha x. So we then have dt is equal to square roots of alpha dx. So this now becomes 1 over the square root of a, the integral from 0 to infinity, the bounds don't actually change here, and then e to the negative t squared dt. Now this is just the Gaussian integral. The value of this integral right here is equal to the square root of pi over 2. And you can calculate this on your own as well by multiplying this and then doing I squared and then converting into polar coordinates. However, we're not going to do this, we're just going to use this result here. So we know that this is equal to the square root of pi over 2. So this gives us I prime of alpha is equal to the square root of pi over 2 square root of a. And let's rewrite our initial condition I of 0 is equal to 0. So before I move on, let's first confirm that this is going to be able to find us the value of I. Really, we have an alpha here now, and we have an I of alpha here. And we want to find the I constants here. So really what we're going to be finding is I of alpha equals alpha. We're going to let this, and we need to find alpha such that, so we want to find alpha such that it satisfies this right here. And then we'll know that will be the value of I. Okay, so now let's proceed, and let's integrate I prime of alpha. So we'll get square root of pi over 2 times alpha to the 1 over 2 d alpha. So this is negative 1 over 2, so we have square roots of pi over 2 alpha to the 1 over 2 times 2. 2's cancel out, so we get square roots of pi alpha plus c. Okay, so now we need to know what our c is. So we have I of 0 is equal to 0 is equal to square roots pi times 0 plus c. This is just c, so we now know that c is equal to 0. So now we know that I of alpha is equal to the square root of pi alpha. So now what we can do is we can find out when I of alpha is equal to alpha. So we convert this into an alpha. So alpha is equal to square root of pi alpha. Let's square both equations. We'll get alpha squared minus, square both sides, sorry, minus pi alpha equals 0. Alpha minus pi is equal to 0, and alpha is equal to 0, or alpha is equal to pi. This is the same as our values for I, so I is equal to 0, or I is equal to pi. We must find the non-zero constants such that I satisfies the equation from before. So I equals 0 is an extraneous solution. It's not one that we need. So this is our actual answer. I is equal to pi.